Hello, everyone. My name is Giacomo Barbieri from the University of Los Andes, and I'm going to present you today a work that we did with the Politecnico of Milan and Tecnológico de Monterrey, which is called a case study from problem-based learning education in fault diagnosis assessment. So I'm going to start with the introduction and then with the theoretical framework that we use for this case study. Then we will present you our unbalanced shaft case study, and then we will conclude with the resultant discussion and conclusion and future work. Concerning the introduction, we have that this work deals with maintenance, and in particular, we know that we have three main maintenance strategy. So breakdown maintenance, in which no action are taken to maintain the equipment until it breaks. And in this case, we have some benefits, which for sure we have a low cost because we don't have a policy for maintenance. But on the other side, we have high time and a high spare inventory. Then we have preventive maintenance, in which we have maintenance on a time or usage interval, regardless the actual state of the asset. And we have a lower than time, but on the other side, since we can plan maintenance, but on the other side, we are not robust to random breakdown, and we have a problem in which we limit the asset life. Eventually, we have predictive maintenance, which is a sort of preventive maintenance program driven by the condition. This has the benefit to increase the asset life, to reduce downtime, to reduce spare part, but on the other side, we have more cost and complexity on the system. In the domain of predictive maintenance, we have three different types of task, which can be health assessment, which consists in estimating the health state of our asset, diagnostic, which consists something that occurs after the fault has occurred. So we have a fault detection, isolation, and classification. And eventually prognostic, which consists in the prediction of the asset health condition, including also the prediction of when the fault is going to occur. In this case study, we will deal with diagnostic. And in general, predictive maintenance nowadays is performed through sensor, and we talk about condition-based maintenance, which is we attempt to monitor the machinery health state by using condition measurement that do not interrupt the machine operation. Therefore, we talk about condition-based predictive maintenance, which is predictive maintenance using condition-based maintenance techniques. And this tendency has increased of condition-based predictive maintenance with the advent of the Industry 4.0, in which we have a lower cost of sensor and more possibility for data acquisition, gathering, storage, and processing. This domain, therefore, becomes fundamental that students start to acquire knowledge, also engineering students, in condition-based predictive maintenance. While in the other domains, the other strategy of maintenance, we have quite a lot of material in education, since it's a lot of years that this strategy are being utilized. We have very few material here. So our idea in this work is to develop a case study that can guide students to learn condition-based predictive maintenance. And in particular, our case study will deal with the fault diagnosis assessment, which is the diagnostic through condition-based maintenance techniques. Concerning the theoretical framework, we will use problem-based learning, which is a student-centered approach in which student will basically self-directed learning strategy, collaborative learning, and also strategy in which learning is related to practice. The idea here is to develop a viable solution to unstructured problems. So problems that already are formalized with requirements and so on. The benefits shown in the literature are long-term retention of the concept, better skill development, and also a better satisfaction of students and teachers. The problem, what is the drawback, is the problem itself, because the problem needs to be large enough to apply all the different concepts that are trained in the course, and also need to be quite a real-world problem, let's say close to real-world problem, in order to engage students. Generally, the workflow for problem-based learning is problem analysis, in which the student analyzes the problem to be solved, identify what they need to learn, in order to solve the problem. Then there is a self-learning stage in which they learn the identified concept, and eventually we have the problem solution. On the other side, we need to also learn, apply the workflow for solving fault diagnosis assessment problem, which here we have a criticality analysis in which we want to identify what are the failure modes of an equipment and what are the critical components in which to apply fault diagnosis assessment. Then we have the collection of data, and this involves also the selection of which sensor we utilize for this. So for example, we can have vibration sensor, temperature sensor, and so on. Then we have the data acquisition, gathering, and then the processing, which is divided in pair processing, in which we want to correct some errors on the data, like outliers, like zero drift, and so on, filter the data in case we have noise, and we want to extract the feature of the data, which provide us some characteristic to classify the fault, and eventually the smart processing for achieving a classification of the data. And finally, we have the data visualization in order to support the decision-making process. Therefore, our requirements that we identify for our case study on the fault diagnosis assessment in education are the identification of a problem based on a real-life scenario, a problem that allowed the application of fault condition-based predictive maintenance workflow, a problem that is provided that the assessment in an objective way, which is quite difficult sometimes when we have a problem-based learning. And also we want to use an information system that allows the gathering of the data that can in this way used by any university. So we developed this unbalanced shaft case study, which is based in an induction motor test bench, in which we have an induction motor with a flywheel, and we manually unbalance this shaft with 5 levels of unbalance by using screw and nuts. In this way, the student, what they have to do is acquire data, use the data acquired from a vibration sensor to classify all the different levels of unbalance. For this, we have a vibration sensor placed on this bearing, which is the sensor shown here, and we acquired data at a sampling rate of 1000 hertz. We acquired 20 samples for each unbalanced stage, so in total 100 data sample. And for the data gathering, we gathered this data on a CSV file. Then we upload this data in Xrepo, which is an information system that we created to label, store, and selectively download the maintenance data for predictive maintenance analysis. And we divided the data into 2 samples, so 90, which were labeled with their unbalanced condition, and 10 unlabeled. So the idea of the student is that to apply machine learning algorithm to train a model for the automatic classification of the 10 unlabeled data. Then we did the data pre-processing, in which we have the analog to digital conversion in order to move from a voltage signal to a signal of acceleration. Then we correct some error like zero drift. We remove the transition behavior since the data were characterized by a transition behavior and a steady state behavior. And then we notice that we have some noise, and we know from the domain that the unbalance can be seen on the motor frequency, which in our case is 28.5 hertz. So what was outside this frequency is noise. So we design a Butterwood filter to remove all the noise components. From that, we calculate we extract feature. In particular, we extract features on the time domain, since we can notice here that we have the bigger level of unbalance and the lower, and we can see that the amplitude change a lot from one to the other. And also on the frequency domain, we calculate the value of the amplitude at the motor frequency, since from the domain we know that the unbalance can be seen at the motor frequency. By doing that, we can see here, we normalize the feature from 0 to 1, and we can see that we are able to basically separate the different levels of imbalance. And what we did in order to generate an automatic classification, we apply a key nearest neighbor algorithm in which we use Euclidean distance as classification metrics. And then we use the F1 score in order to detect how well was able our model to classify the unknown data. Here we can see the training data and the unknown data in a white circle. So we can see also visually that our model is going to be able to classify perfectly all the different levels of imbalance. And so it's not surprising that the algorithm reach 100% of accuracy. So as you can see, the development case study was close to real life scenario, since we use an induction model which is quite widespread in the industry, and imbalance consists in 5%. It is estimated of the failure in this application. This case study allows students to perform all the workflow typical of condition-based predictive maintenance. Moreover, we have different steps, and at the end, like a matrix, which is the F1 score that allow the assessment of the student in an objective way. And eventually, we use this information system, which allowed the widespread the share of the data with all the different universities that may be interested in this. What we saw in this is that this case study can also help in the try to let's say cancel wrong beliefs on students that sometimes with the advent of Industry 4.0 and all this data-driven methodology, people may think that domain knowledge is not necessary when data-driven models are used, but we can see that if we reach 100% of accuracy is because we start from domain knowledge, since we know that imbalance can be seen with, for example, at the frequency of the motor in the frequency domain. And on the other side, another strong belief that all these Industry 4.0 tendency can generate on students is that all the maintenance problem can be solved with sensor and data-driven model, which is not always. This is something that is a cost-benefit trade-off, since we know that these technology are generate a cost, and also they need maintenance itself. So, for example, the sensor need to be calibrated, can have breakdown, and so on. Therefore, the idea is, let's say, to start making students think that not always placing a sensor is the solution. For this, what we reached was to generate a case study that applied based on problem-based learning, which showed the integration in between domain knowledge and data-driven model, close to real-life problem, which is able to assess the student with an objective metrics. The case study is available on ResearchGate, since we still need to improve our X-repo information system. And what we want to show you maybe here with this paper is there is the need of data set of education in predictive maintenance. And we hope that with this paper, we probably start to impulse this research area. What will be the future work? Probably is we need like a case study for maintenance policy selection, because we know that condition-based maintenance is useful in particular for assets that have quite a low failure rate but high downtimes. Therefore, it would be very useful to develop a study in which student is going to train on the to select one or the other maintenance policy on the basis of the study case study. And eventually, we want to go on the development of this platform in order to generate an information system to boost, let's say, education in predictive maintenance. So thank you very much, and I'm really looking forward to solve some doubt and curiosity concerning this. See you.